All right, you ready?
Yes.
All right, because I spent the whole weekend trying to do my notes over again because I hated them. So we're going to see what happens. And then we're going to get to a point you're like, yeah, you should have went bowling or something because that didn't work. So the first part of this here lecture is not going to have me writing anything in notes. So you need to take notes.
I don't think you're recording.
I am.
Are you?
But thank you for asking. See, now I got to edit that part out.
Come on, Adam.
All right. He's like, oh crap, then I better. He's not writing it. All right, so I'm not going to write stuff down. That's going to be up to you to take some notes until I get into that. All right, we're going to talk about generators, alternators, and motors. All right? All right. Purpose of a generator or alternator, not motor. Purpose of a generator is to
convert mechanical energy into electrical energy.
How did you guess that?
Call it a hunch.
It might also be the name.
Although he said that and the rest of the class going, how did he know? It says it right here. All right, to convert mechanical energy into electrical energy. So we're going to drive a generator and or alternator. We're going to talk about generators first. Generators are the old-timey things before alternators, before they could figure out solid-state components such as diodes. You need diodes to run an alternator. So before diodes, there were generators, and generators don't work as well as alternators, and we will get into that. But you take a generator, which is typically either driven off the engine. Lycoming tends to put them down here on the bottom and drive them off of a belt. Continental tends to run them off the back of the engine off a gear drive, or the newer big bores, 720s, 720. Geez, I'm all over the place. 520s and 550s, because Lycoming is the 720. The Continental big bores, IO, TSIO series 520s, 550s, they actually run them off the front of the case. They extend the case out a little bit. It looks like there's 1, 2, 3 cylinders and a smaller cylinder when they're disassembled, and that's where the generator goes. And they've had all kinds, or alternator, all kinds of problems with that. Here is one right here. I don't know if you can see it very well, but
Wind turbine.
it's a wind turbine. They just basically took a generator and a hose clamped it to the gear legs on the airplane, put a little spinny thing on it, and ran some wires up there, and that's how they made a generator go. So wind-driven generator. Send
They
it.
still do those too.
Oh, absolutely.
Yeah, they do those on like the Airbus, but isn't that more for like a hydraulic, like auxiliary hydraulic pump?
As far as I know. But I've worked on small airplanes. I remember I got a Luscombe in one time and had there was an alternator on the front with a Toyota fan on the front, because they have like the blades aren't completely symmetrical. I'm like, what the heck? And it was an STC, although the person who put it on, it goes, STC. I don't know what that means, but I'll hang on to it and bolt this on the airplane. And so I had to do paperwork. All right. This is a repeat of what we've already discussed, although I probably didn't say that because I don't think a lot of you remember this. How is voltage induced in a conductor? Or we could say, how is current induced in a conductor? Same thing. We've got a voltage and current. How is it induced in a conductor? We need 3 items to generate current flow. That is something I would want to write down, because I'm going to ask everybody in every oral from here on out for everything. I'm going to ask it for magnetos, generators, alternators, and what's that?
Relative motion.
We need 3 things. Well, let's see if we can work. We need a magnetic field. What produces a magnetic field?
Magnetic fields.
Well, he got it first. Magnetic fields. Produce magnetic fields. What produces a magnetic field? What?
Permanent magnet.
Permanent magnet, or
Electromagnet.
or an electromagnet. Do we have any other kind of magnets? That's pretty much it. Yeah, we'll kind of lump that into one. Either a magnet with like that, or electromagnet. All right, so we need a magnetic field produced by either an electromagnet or a permanent magnet. We need a conductor, which is a wire or a coil or whatever. It's however that conductor is. Straight, curved, whatever you want. And we need
Relative motion.
relative motion, where that goes.
Cuts across the conductor.
Thank you. It cuts across the lines of flux. So the conductor or inductor, what's the difference between a conductor and an inductor?
Conductor conducts electricity and inductor does not.
Induction is the
Coil of wire.
Yeah.
Inductor is a coil of wire. The conductor is just a piece, straight piece. So I don't know if you have a conductor, inductor, whatever you like, but you got some wire there. That's why I said be straight, coiled, whatever. And we have to have relative motions. We got all three things: magnetic field, conductor, relative motion.
And once again, the collapsing of the magnetic field also counts as relative motion. Right?
Yes, collapsing of a magnetic field counts. But in this case, we could move the magnets or we could move the wire. It would not matter as long as there's relative motion. But this is very inefficient, trying to move a piece of wire up and down inside of something. So we're going to create something that's actually usable. And we're going to loop the wires so that we could, in fact, rotate these wires. So we're going to loop the wire. Once we loop the wire, like we've done like that, it becomes, and we call it an armature. And we're going to add brushes and rings. What are brushes?
Like carbon brushes. that go
Carbon
around.
brushes. You guys work on your magneto. How many brushes does your magneto have? One. All right. But now we're going to have two. One right there and one right there. So we have two carbon brushes. Going against some rings. We often call them slip rings in this application. And we're going to rotate this armature. Everybody good to move on? All right. Problems. Oh, yeah. We are making a what? A generator. A generator does what? Converts mechanical to electrical. What kind of electrical energy does it create?
AC.
Ooh, generator generates and puts out DC. So that is a DC generator. So we are working on a DC generator. So we need it to have what kind of output? DC. So this is, well, there are many, but primarily this will produce.
AC.
And would we want AC?
No, we want DC.
So that's all an AC generator is right there. I'll be done. So how do you make an AC generator? Well, take a loop of wire, put some slip rings and some brushes, and start rotating it, and you've got AC generator. They're easy to make. And so what that would do is, well, I'll show you when we get around to it. So voltage varies with position. So we got to know the voltage of this wire, and the voltage output is going to vary with the position. The greatest voltage occurs as a conductor passes at what? Right angles. So when it's right in this area right here, I'm going to move to this right in here, when it's moving up through these lines of flux. I don't know if you can see the lines of flux. They're kind of blue on gray. I didn't redo this part this weekend, so this is old stuff. When it goes through there, it's doing what through the lines of flux? Cutting across. So as it cuts across the lines of flux, we will get what induced in the armature, which is the loop of wire? Current. All right, the amount of current, I don't know if I have this written down here anywhere, the amount of current will be dependent upon the speed of, well, a couple of things. One, how strong the magnetic lines of flux are, and two, the speed at which it cuts those lines of flux. So flux density is what it's called, plays a big part. So the more flux density we have, the more voltage you're going to get, and the greater speed at which it cuts will give you more voltage. So we want stronger magnet, more speed, right? To a point, because we're going to have to control it. So the greatest voltage occurs as the conductor passes at right angles to the lines of flux. So we've got the greatest voltage there. And the least amount is going to be when?
At neutral.
Up here at the top, when the armature is running parallel-ish. The least voltage occurs as the conductor passes parallel to the lines of flux. So as we rotate this armature, we're creating what kind of electricity? AC or DC? AC, alternating current, because it is going to look, well, I guess we're going to get into something else first. That would just look like the static flux curve that we're used to seeing. All right, we good? Okay. In order to understand this, we have to understand which way the current is flowing, and that's where we go back to our left-hand rule of thumb, our gang symbol for the class. Thumb points in direction of motion. This is the field going from, magnetic field going from north to south. Make sure you're paying attention. And the third one going this way is the direction of current flow, conventional or electron? Should be electron. Electron. All right. So using these things, we can take a look at something like this. We can figure out which way the current is going to flow. So which way is current going to flow? So it's going north to south. Direction of movement. So the stick, is it positive to you or negative to you? Which is coming out of the board?
It's coming out to us, so it's negative. Or it's positive.
Positive. It should be positive coming out. So positive, that's negative. There we go. All right, so we keep that in mind. And we're going to look at this, and that's how we determine which way the current is flowing through this. I'll enlarge it just a little bit. Applying the left-hand rule, as segment A moves up, so this is rotating this way. A is moving up and around, going this way. So A is moving up. We use the left-hand rule of thumb. Just trust me, I'm not going to sit there and do it because I think it's backwards for me. That means the current is going to go A to B, down through here, through this slip ring. Can everybody see that okay? Yeah, okay. Out through here, through the load, back in the slip ring and around. So that's when A is over there on the left-hand side. But what's going to happen next is now A is over on the other side. So A did a complete 180. A is now over here. And we do the left-hand rule of thumb. We're kind of going backwards, and we got B going the other way. And that means that current is now flowing still around this way, but A is down over here. So A is going to come this way to this bottom slip ring, through this way and around. So everybody kind of see how that's working, and you believe me. And so as we rotate that, there we go, both sides. Kind of taking a look at once. Let's see if I can. There we go. So when A is over here on the left, current is flowing from point 1 to 2. And when A gets to the right, it's going 2 to 3. And that is because of the way the slip rings are on there. So A comes around here, comes, let's say, out of B to the first slip ring. But over here, it goes around B, comes out of A, which comes down to this slip ring. The A does not touch this slip ring right here. It comes down to here. So everybody follow so far, because it's important. And the amount of current that we can make in this loop of wire, called a what?
Armature.
Is dependent upon what two things so far?
Flux density.
Flux density and
Flux density and speed.
speed, because speed represents how fast we're changing. Or cutting across, I should say, cutting across. All right.
So flux density is like a more powerful magnet.
Flux density is, even a weak magnet has flux density. It's just the greater the
You're
stronger
right.
the magnet, the greater the flux density.
That's
That's what I figured. This reversal of current flow produces what?
Alternating current.
And we want to make what for the generator?
Right.
All right, because it's a DC generator. Good. Recache. Greatest voltages produced as a conductor moves at right angles to the lines of flux, which is going this way. Left-hand rule shows us current is reversing direction. We looked at that, and then we can understand that, hopefully, that once we do this, we are making alternating current. If we look right here, this loop of wire is straight up and down, going this way, which means it's what to the lines of flux? Parallel. Then it goes this way. It's maximum register, we could say, right here, maximum. Reaches a maximum, and it's going positive, and then it gets this way, and it's back to 0. I'll go this way. And then it goes around again, and then we're swinging down negative. All right. Back to 0. So we've made a what?
AC
Sine wave.
generator.
We made an AC generator with a nice little sine wave, but we want DC. All right. Oh, good. There's going to be a solution. I was hoping so. All right. We're going to add a commutator. So what we've done to make a commutator, I'm going to back up. We're going to take those slip rings off. We're going to make, I'll go back. Let's see so you can see it. We're going to basically cut the wire, take off both slip rings, throw them out, and now we're going to put and even out the armature so everything is the same size, so to speak. And then we're going to put a half moon slip ring on there. So you can see that's half and then half and a space in between. And what you're seeing right there is just the brushes are resting right in between the two. They're not touching anything. So we got this half up here, this half over there. You can look at it here. You've got a half with the brush on it. Over here, same thing, half brush on it. So this is going to be a commutator. So what is a commutator going to do?
Convert from AC to DC.
Mechanically convert AC to DC. There we go. So again, the AC output, we have the two slip rings. This part right here, if you're trying to make sense of it, we have the magnet and the armature in it, but it just shows the slip rings down here. We change that and put it over here. We make a commutator. Everybody's with me on a commutator? Commutator is something that mechanically is going to convert AC to DC. Well, let me show you how it works. So looking at this up here, we'll kind of zoom in on it, and we will see that as loop A, B, C, and D now. We're going to do A, B, C, D. So I don't know why, because it's a different book or something. But you can see in this position, what do you expect the output to be?
Zero.
Zero. All right, so we're right there at 0. Then when it swings this way, we've got DCBA coming out of A and around. It's going to this brush here. We'll make that the negative. Comes through here. Light's getting it back to positive on this side. Follow? Okay, so that's full. Then, of course, we got to come back around. We're going to get neutral again. But, all right, I'll try and keep these both on here. So now A and B went over to this side, and D and C went over that side. So where before that switched the whole sine wave, now let's take a look at it. So, again, it's going the same way because of the left-hand rule of thumb. It's always going to go this way on the south, out this way. It's coming around here, but we're coming back to a commutator that's in pretty much the same spot as the other one instead of going to a slip ring that's in the longer or shorter. And that means now this is on the negative side, so it's just going to come through the load that way. So you can see how it continues then to go, no matter what, it's going to come this way to this brush right there. So that would be my negative brush. Every time that commutator segment comes around here, that's negative. And what we end up with is that.
McDonald's.
Positive.
A what?
McDonald's and
Well, never.
2 arches.
Positive. So it's always positive.
So since it's a split ring, it's going to always stay. It's isolating basically the positive and negative sides.
Yep.
So all they did was just take a slip ring out and just made the two connect to one. Basically.
Sure. Take a slip ring out, cut it. Now you got to have that cut in there because you can't have positive and negative all together. See the little cut right there. All right. And so this side over here to the right is going to be the negative side, and the side over here, the right, is going to be the positive side. No matter which way that loop of wire goes, the one on the right is going to be the negative side. The one on the left is the positive.
Well, the current flows.
Yes.
So this is what we would get chopped DC from? practically?
Exactly. Yeah.
Okay, so.
I don't know
even
about
though it
chopped
shows
is
it
the word.
as
It's
the
the,
sine wave, it'd be more like.
this is more like rectified DC here.
Okay.
All right. Follow?
I have a question.
Yeah.
Does the commutator, is it moving with the armature?
It
or
sure
it
is.
stationary?
It's welded to that wire. Or that wire is kind of soldered onto it. So the commutator is going around at the same time that so that this, I don't know, CD part is always connected to this piece and the AB is always on that piece.
That makes sense.
I forgot to bring in all my toys. No, I didn't. I brought them in the other day. So here is an armature. with. So when I turn the armature, what turns with it?
The commutator.
Commutator. It's
It's got a lot.
part of the windings. Now, of course, this has a lot of windings, not just one. That's what we're getting to.
That helps smoothing it out.
Yes, it does.
Not gonna show that movie?
What movie?
It's on the canvas. You put it there. The older
The army
like,
one.
Huh?
The army one.
Yeah.
Oh, no, show that now. You can watch it. I get paid to do this. I don't do that. All right. So how are we going to prove the output? Right here. By adding multiple windings and a commutator segments to the armature, the resultant output is a much better DC voltage. So you can see right there, the solid line is where it's going to get picked up from. Well, how do they pick it up from that? You have all of these commutator segments, and as it rotates, you have brushes that are going to be aligned in the right spot. And so as the voltage starts to drop off on one, it'll just rotate and pick it up off the next segment. Get that little half wave, and then that starts to go away. And then by then, the commutator segment switches to another brush, and it just kind of keeps going around. So that the brushes are always, so to speak, peaking up on the peak right there. There's a sweet spot. Obviously, we know that the brushes going up and down have zero voltage. So if I move the commutators like this way and tried to pick it up off the ones that are on the top and off the bottom, then I would get pretty much just zero. So you got to have it in the right spot for where you want it. So voltage still produced, just not used. Let me know when you're done writing. Good? Huh? Who said no? Okay. How about now?
So the armature is pretty much just the assembly itself, or you call that each coil?
This is the armature assembly.
Okay.
So yeah, as opposed to is each one an armature? No, it's an armature assembly. All right, moving on. Okay, yay. What have we learned so far? What's a generator?
Turns.
All right. All right, what are the three elements needed to produce voltage that I'm going to ask you from henceforth on every single oral?
Magnetic field, conductor, relative motion.
All right, conductor, magnetic field, relative motion. What is the function of the commutator and brushes?
Mechanically versus DC.
AC to DC.
This, to change the voltage output of the generator from AC to DC. AC being alternating current and DC being direct current. We didn't know that yet. What is DC again?
AC/DC, isn't that a band?
Dumb and confused and articulate and confident.
What do the brushes do?
All right, good question. What do the brushes do? Just like in the magneto, the brush is a carbon brush, and it is something that allows this to slide against it and transfer electricity from this commutator to the brush, which picks up the electricity, then goes to a wire. It's just like you couldn't put a wire on here. I mean, you could, it wouldn't last long, so we use brushes.
We use carbon because it's high wear. It's wear resistant.
Yeah, and I think it adds a little bit of lubricant. Left-hand rule of thumb. Oh, nobody cares about that. Objectives. I used this slide when I interviewed for this position, so I had to do objectives and all that good stuff, but nobody cares. All right. So there is well, I guess we could look. What am I supposed to teach you about? The neutral plane, armature reaction, interpole, and that's easy. All right. So we have the neutral plane, which is just another fancy word for where there isn't any voltage induced. And you already know that that's going to happen up here at the top when the armature, the specific loop. So when I say the armature, I could be talking about this, or in my case, I was talking about the loop of wire. So when the loop of wire of the armature is going parallel to the lines of flux, then what kind of output do we have? Zero. That's the neutral plane. So a position which no voltage is induced in the conductor. Well, we want to know about the neutral plane because we have to know where it's safe to put the brushes. If we put them in the wrong spot, what we end up doing is shorting out the armature every time it cuts across one of those little spaces in there. So we need to know where to pick it up and where not to. So here we go. Any shift in the position of the magnetic field of a generator causes a shift in the position of the neutral plane. Well, it would be nice if the neutral plane was just right there at the top and the bottom, which if this was static and turned off, that's exactly what it would be. It would be right there where these little dots are. But because we are going to be rotating a loop of wire in here, and what does that loop of wire have running through it?
Current.
And what happens to a loop of wire that has current running through it?
Induces a magnetic field.
It induces a magnetic field. So now we've got a wire with a magnetic field running inside of a magnetic field. The two, and remember, when we start dealing with fluxes, they don't cross each other. They don't. Anyway, you're going to get an interference between the two magnets. So that interference is going to kind of mess things up. So any shift in the position of the magnetic field of a generator causes a shift in the position of the neutral plane. So here we have the wires in the, I don't want to say full register, but
Close to the poles.
yeah, close to the poles. I was trying to think of the word I wanted, but not full register. But anyway, these have magnetic field now running through them because it's rotating. We just looked at it. So what happened to the field here?
They twist.
It twisted and got all messed up. Yes.
Would it be north to north and south to south, or would they be polar opposites?
These wires?
Yeah, with the wires, would it?
Oh my goodness. Yeah, we'd have to get into one of the hands rule of thumb to figure out which is north, which is south.
Okay, just,
It's-
in case the
it's not even
magnet was attracting the wire, or repelling
It's
the wire.
not relevant. You know, then I just start making. Sometimes I worry if I get too deep into the woods, people focus on the wrong thing. And then I ask them, you know, it's like, oh, I didn't study that part. And I'm like, why would you study that? So we'll keep it simple and say it doesn't matter if that's a north-south or north-south. What's important is that a magnetic field in the loop of wire caused
A
magnetic
shift in the
magnetic shift. Well, that just changes everything. And let's make it worse. The more current that flows through these wires, the worse it's going to get. So we can't even look at it and say, well, it's going to look like that. So just put the neutral plane over here at this point and the neutral plane over that point, we're done. Right? If no current is flowing through the armature, or very little, then it's going to be relatively straight. And the more current that flows through the armature, the worse it's going to get. So it's a constant shifting thing. Shifts in the magnetic field are caused by a change in the load. Hey, I just said that.
changes
Good
with
for me.
speed, too.
Everything. Well, of course it's going to change in
Well, with the
speed.
more current flowing through it.
Yeah, but we have to remember the ultimate goal is we have to regulate the generator. We can't just let it do its own thing. So we can't let it speed up and generate more. We're always going to have to,
Limit it.
just like a bad student, shut it down. All right. Well, this is because as current flows in the armature increases, so does the magnetic field through the armature wires. This causes a shift in the magnetic field. Well, I just said that. And you probably already wrote it down. We good? Tom? Yeah? Yeah? I told you I need a pace car. I always need a pace car. That's you? That's fine. I always got to pick one student who's my writer and see. You good? All right. I have no problem waiting. All right. So there we go. Neutral plane shift before was nice. Now it's not because we have armature reaction. So it's just a representation. I don't know if there's anything to write down with that. All right. So as brushes cross segments of the commutator, they short them out. Which is to say that if I, had a commutator segment and a commutator segment there, and I said, let me see, black, and I had a carbon brush, and it's right there, and another carbon brush right here, and this is the positive side, and that's the negative side. What did I just do to it? I shorted the whole thing out, right? And that's a problem. So the only time when it's really safe to cross the street, so to speak, is when the segment is in the neutral plane, where this is pretty much 0 volts and 0 volts, and then it's happy. Now the next slide, if I'm not mistaken, is a little confusing. So let me see. Is it the next slide? It is. So I want to tell you this. If you understand what I'm telling you right here, you're fine. But you better understand that. Because then, I guess it's not that. It's why do we have interpoles? So that is why we have interpoles. You understand that. The whole reason why we're looking at it in the explanation of where the neutral plane is gets a little bit, whoa, what just happened there? I tend to understand this one here better than I can understand this one, but it's the same thing. So what they've done here is a nice little drawing, and they've just taken the loops and they said, well, let's just look at the voltage being produced in this winding, and we'll call it that. What's the voltage being produced here? We'll put it there. And so they just gave us a battery representation of these windings right here. And so right here you can see that as this brush crosses here, it's at the potential between that spot and that spot is 0. But in just a second, the potential is going to be in their representation 4 plus and 4 minus, which would be 8 volts. Got it? So as brushes cross segments of the commutator, they actually short the circuit then. The only time this is safe is in the segments in the neutral plane, which I think I've said several times now. So you can see it's crossing right there. We're at 0, but in just half a second, a small few degrees of rotation, it's going to be on this segment here, which by this representation be a positive 4. And let me see, it's going to go this way. So this representation be a negative 4, right? Yeah, it'd be on this one right here, a negative 4. So that'd be 8 volts. Got it? Okay.
Could you actually spin that a little bit more?
Did I spin it more?
No, yeah, spin it a little more, explain it just a tad bit. I don't understand it.
And it's okay if you don't necessarily understand this. It is okay. And, you know, I don't often give you permission to do that, but this is confusing. What you have to understand, and the main takeaway is really what I wrote here. And that, maybe not.
Can you zoom in?
Yes, I'll zoom in. See how that brush is right there across that little, this is one segment and this is the other segment. That line going this way represents the break in the two. And because the difference of potential between this spot and this spot, because this is a positive 4 and that's a positive, the difference of potential between those two is 0. So in sense, these two have the same voltage right now. So it's safe to short them out because they're the same. And same thing down here. But as this rotates just a little bit, just this way, then this brush will be completely on this segment right here and completely on this segment right here, which gives me a positive 4 and a negative 4, if you want to look at it that way. And so it'll be riding in the middle. And that's okay because it's not cutting anything. And then in a little bit, remember the brushes stay put and as this rotates. So every time that this split gets to this point, it's going to have 0 volts. So this part right here is spinning. So every time it gets here, it's 0, but it spins a little bit. It'll pick up 4 volts here, 4 volts over there, negative 4 for 8 volts, if you want to look at it that way. So again, it's just all about, you got to put the brush where it's 0 across the little segment. And remember, it's not 0 because it's not producing voltage. It's 0 because this is a positive 4 and this is a positive 4. So these two have the same amount of voltage. So they're not different. So they're not shorting each other out. Got it?
Do those brushes ever? No, the brushes stay there and that moves.
That moves around it.
Yeah.
And as it moves, then the voltage is changing as it goes.
And the voltage is changing. Yeah, this loop isn't always 0. When this loop gets to here, it's going to be 4, right? And when this loop gets to here, it'll be 6. So, all right. And I think I probably oversimplified it because we'd add in voltage across here. So 6 and 4 is going to be 12. So it'd actually get 12 over here. So Yeah, see how here and here it makes 14 volts in just a second. So, well, actually, right at that spot, it makes, you're getting, let's see, from this one is the positive, and you would be getting, we'd have to be getting 7 volts because it's 14. Told you, it's a little confusing, 7. I don't see where they got 7 from, because if it's 14, that's half of 14 is 7.
We have 4, 4, and 6. That's 14, and then each one picks up half.
4, you can't do 4, 4, and 6, because it's got to be even, like 10 and 10. I don't know. Like I said, it's not that important how they did that. Sometimes I get it, sometimes I don't. It's like a confusing one. Follow? Okay. Oh, I know what you're saying. 4, 4, and 6.
Yeah.
So 14 right there. This side is 14. So positive into the negative, positive. So what happens to the voltages?
Zeros.
It adds up. So positive, positive, positive. So we have 3 batteries in series. So what do we do with the voltage? So 4 plus 6 plus 4,
14.
14. So right there we have 14. So they're saying right here, on this one we've got,
14 volts.
well, between here and here we have 14. So, and this is going backwards the other way. So that's the negative to positive. So positive, positive, positive. It's going the other way. That's going the same way.
But it's from
Yeah.
0. It's not the full sine wave. So it's like
Right.
So it's from 0. The difference between 14 and 0 is 14.
Like I said, this is not the slide to get hung up on. It really isn't. What is the takeaway?
That
It's
neutral.
only time it's safe is when the segment's in the neutral plane.
Right. And the reason why I want to tell you that is so that you understand what an interpole is. So to correct for the neutral plane, they use interpoles or compensation windings. So if you look at the drawing right here, you've got the main poles, or the main, these are actually the field shoes. This is the magnet, if you will. So you have the magnet, but there's 4 of them. That's why you don't see north-south. It's north-south this way and north-south this way. So you have 4 magnets, north-south, north. And then in between, you have these little magnets. And in reality, these bigger magnets that we've been saying are permanent magnets are actually electromagnets. That's how we're going to control the entire thing. But specifically, these little interpoles are going to be electromagnets. And they're wired in series with the armature. And that's really important because we know that in a series circuit, whatever current flows through one thing, it flows through the other thing. So the more current flowing through the armature and coming out of the commutator, the more current we're going to have in the interpoles. So where this had current and created a shift, now we'll create current somewhere else that's the same as this to create the opposite shift and put it right back where we want it.
Counterbalance it.
Counterbalance.
Self-regulation.
Self-rate. So the more current we get here, the more current we get in the interpoles.
Who the hell looked at that and was like, yes, this is what I need to do?
I know. And all we have to do is try and understand what they did. They thought of this. So,
If they do
They
it,
made the boot.
so can we.
all right. Interpoles are connected in series with the armature. Therefore, the amount of current flowing through the interpoles is always the same as the current flowing in the armature. There's one other way to do it. I don't think I have it in my notes, but they actually can embed something, I think in the armature in a backwards way, but I don't have that. I don't think the FAA asked you about it. All right, got that?
Not yet. Makes sense here. The movie didn't quite.
I don't
That was
know.
one thing I kind of got pitched up on.
Oh, I don't advocate those movies. I just
That was neat.
I love the old, what's it called? They're I forget the name of them. The old timey black and white military movies.
Propaganda.
They're kind of neat.
The what?
Propaganda films.
No.
Sure.
Sure.
The educational.
All right, interpole has the same polarity as the next main pole in direction of rotation. I don't know how important that is, because you're not designing them, you just got to understand it. So here we go. So if it's rotating around this way, interpole has the same polarity as the next main pole as the next main. That's why I put the arrow so it's screwed up. So south to south, north to north, and you can just see how.
Otherwise, it would distort it more, probably.
Yeah. Let me go back one. Oh, yeah, I got it. So, interpole south, interpole north, interpole, yeah. So, I don't know, the drawing I have here is not, so there we go. Before the load increase, and then after the load increase, what's the difference? Well, this one, you can see the blue a little bit better than this one. That's about it. There's actually more circles around there, and then there's more lines of flux coming out of there. So, just indicating that one line of flux out of the armature, one line of flux coming out of the interpole. Here we have 3 lines of flux with 3 lines of flux. So, yay. All right.
Okay, you got back.
Oh, I did write it. Okay. What? Go back.
Go back one side almost.
All right. Aside from that, and I don't know if this is on the FA Q&As, but I know it exists. Compensation windings or compensating windings perform the same function as interpoles. These windings are embedded in the slots of the pole faces and wired in series with the armature. So instead of having an interpole, you just put slots and then you kind of embed it in the field, the magnets, if you will. You don't write all this. The series connection with the armature produces a magnetic field, and the compensating windings that varies directly with the armature current. The compensating windings are wound in such a manner that the magnetic field produced by them counteracts the magnetic field produced by the armature. As a result, the neutral plane remains stationary. Any magnitude of armature.
Same thing as interpole.
It's same thing. It's just you could put, and also compensating windings embedded in the slots of the pole faces, which is the magnet faces, if you will, for right now.
Which one might be a little bit more common, the interpoles?
I think interpoles, but I'm not totally sure. Because almost all books talk about interpoles. Not many.
Probably more money.
I gotta kind of be honest with you guys here. I don't love the FA textbooks. I really don't. Not only do I find some errors in it, but they're just laid out so bad. To me, they're not very linear.
How some of the wording is kind of.
Yeah,
They're gonna watch that on YouTube and get mad at you.
they can.
I got a
I'm
buddy
okay with that.
who's self-teaching using the FAA books right now.
Yeah,
He's still in service, and he is hating the book.
there's not that I'm a proponent, but McGraw-Hill series. Oh my God, they're so good. The difference is the FA textbooks have a much lower grade level of reading, and the McGraw-Hill is more of a senior in high school, R level, junior college level of reading. But if you can handle that, they work fantastic. So I can actually stop the recording.